Good afternoon from the KLX studios in Berkeley, California. I'm Frank Ling, and this is the Berkeley Groks Science Show.
That's right, it's a weekly look at the world of science, technology, and their effects on our daily lives. I'm Charles Lee.
Coming up on today's show, bending light and inertial selective reaction.
In addition, we'll be joined by Professor Dan Hooper, who will talk about dark matter and energy.
Also, we'll find out what the Eye of the Orion is.
So stay tuned for all this, plus the Grokatron 5000 and the world-famous question of the week, coming right up here on the Berkeley Groks Science Show.
Welcome back to Berkeley Groks. I'm Frank Ling.
And once again, I guess that makes me Charles Lee, the voice of time travel.
Were you sent back to save us from ourselves?
Sent back to save you from Arnold Schwarzenegger.
Oh, thanks.
Green SUVs.
I gotta get one of those. So did you come here by accident? We're supposed to go back to the 1800s and stop Napoleon.
Well, much like Philip J. Fry, I was delivering a pizza and fell into a cryogenic freezing chamber. Somehow that sent me backwards in time. I'm not sure how that works. Such is life.
Maybe your atoms reach 0-point energy or something.
It might be quite similar, in fact, to the way that light can bend in a negative refractive index.
Ah, indeed.
As if that were a very poor excuse for a segue, here we go. It's the story regarding a way lenses can actually be used to bend light backwards, in a sense.
So we can really see the past or the future.
Perhaps you can even see what your own backside looks like.
I've always wondered. Well, actually, I don't want to.
From this perspective, probably you're right. I'm sure most people know about general ways a surface medium can actually bend light, phenomenon known as refraction. So, for example, if you just try sticking a pencil in a glass of water, you can see that the light bends it.
Right.
So, actually, what happens if you replace this water with what's known as a left-handed material, it'll actually bend the ray so much that, in fact, travels all the way around, so it looks like it actually kinks and backs under itself.
Huh.
Term negative refractive.
Is this a liquid or is it?
Some sort of material, but it's actually quite difficult to actually create these type of materials. Previously been shown for microwaves, and now physicists at the California Institute of Technology, Henry Lezick, Jennifer Dione, and Harry Atwater, have created a material which is basically 50 nanometer thick layer of insulating silicon nitride, which is sandwiched between silver on the top and gold on the bottom. And this is apparently
Expensive stuff.
yeah, well, I don't think you're going to be able to run out of the corner drugstore and grab it, but basically when light interacts with this material at proper wavelengths, it creates what are basically termed as these ripples that run upstream against the flow of the light, which produce the negative refractive index. As they suggest, can lead to all kinds of novel optical materials.
So military must be quite interested in using this stuff to camouflage the various equipments, huh?
The military is interested in anything that could potentially be used to kill. This flat device works only for light traveling in the same plane as the slab.
Okay.
But even so, any advance could lead to optical systems on a chip, for example, or it could be made to have 3D materials that bend light coming from any direction. So
very cool.
It's still at a very preliminary stage right now, but still a lot of work to be done.
I'm sure one day it'll be in the iPhone.
Everything will be in the iPhone one of these days, even your soul. It's published in a recent edition of Science.
So speaking of past Caltech and science, an old friend actually now appears in the news again.
Who is our old friend?
Professor David Macmillan.
Ah, David Macmillan, the great Scottish chemist.
Who's now at Princeton, and he holds the A. Barton Hepburn Chair of Chemistry.
Wow, that guy gets around. I remember,
First he started here, right?
yeah, I remember he was just an assistant professor here at Berkeley.
His humble beginnings.
Yes, hired away by Caltech, I believe.
Yeah.
And now head of a department at Princeton.
Director of the Merck Center for Catalyst.
Yeah, that's impressive, but it's not Harvard.
He did go to Harvard, by the way.
Yeah,
But,
that's his first strike against him, but
I guess his cool new paper, which came in Science, now suggests that there is a way to create catalysts inexpensively for numerous inertial selective reactions. These are the ones that select for a particular chirality or mirror image of a molecule so that you get one form but not the other.
right,
Famous example is thalidomide. The mirror image or its evil twin causes birth defects.
right. Whereas the other one is useful for
Morning sickness.
right.
In his new paper, he says that we can do these with organic catalysts. So until now, most catalysts they use for these reactions required a metal, which were either very expensive or toxic or just very difficult to use. But he now describes a series of these organic molecules, just completely organic catalysts, which seem to do the same job and could potentially bring down the price for creating lots of cool drugs out there.
You know, chemists are always coming up with brand new molecules. Why can't they come up with one that helps me get a date?
Well, Japan actually sells these ties that have pheromones laced in them.
Oh, well. They're in tune with our primal nature.
Yes. Anyways, this was reported in Science.
And that's all for a look at recent developments in the world of science and technology. This is the Berkeley Groks Science Show. Well, coming up in just a few minutes, Dr. Dan Hooper will join us to discuss dark matter and energy. So stay tuned. Welcome back to the Berkeley Groks Science Show. Well, the material world seems permanently solid, but new findings from physics suggest that the ordinary matter we know of comprises just 5% of the total matter. The remaining 95% is comprised of dark matter and dark energy. Well, what is the nature of these mysterious forms of matter and energy? Joining us today on Berkeley Groks to discuss the mysterious world of dark matter and energy is Dr. Dan Hooper. Dr. Hooper is currently the David Schramm Fellow at the Fermi National Accelerator Laboratory. He's the author of numerous scientific publications in prestigious journals, such as the Physical Review Letter. His new book, Dark Cosmos, In Search of Our Universe's Missing Matter and Energy, explores this new issue for a general audience. Dr. Hooper, thank you very much for joining us today on the Berkeley Groks Science Show.
It's good to be here.
Well, this is certainly a very fascinating issue, and maybe before we get into what the dark matter really is, maybe we can talk about what is normal matter.
Well, if you think back to your high school chemistry class, you learned this thing called the periodic table, which basically describes all of the stuff we're familiar with around us in our world. So if you look at the desk in front of you, your car if you're in your commute now, or the air around us, our hands, our bodies, our planet, all this stuff is chemical elements, which are all made of three things: protons, neutrons, and electrons. And that's basically the whole world we know. The really interesting thing about modern cosmology is that we've used it to learn that that's only a 4 or 5% or so of the total energy and mass in our universe, and the other 95 or 96% is in far more exotic stuff that we call dark matter and dark energy.
What is the evidence from cosmology that suggests that this dark matter and energy exists?
So we've known that dark matter exists for quite some time now. The evidence became pretty compelling back in the 70s. The way you do this, or a way you can tell that it's there, is by looking at the way galaxies rotate. So when a planet revolves around its star, like our planet revolves around the sun, we can tell how heavy the sun is by how fast the planet spins around it. The faster it spins around it, the more gravity there must be holding in its orbit, and the more heavy that star must be. Similarly, when we look at the Milky Way or a different galaxy and look at stars moving around the center of that, you can use this to essentially weigh the galaxy itself. And when we do this, we find that only a tiny fraction of the total mass of the galaxy is in that visible stuff we see, like stars and planets. The rest is in something invisible that we call dark matter.
I see. And the dark energy, how do we have a feeling of where that's coming from?
So to understand what we mean by dark energy, we have to go way back to Albert Einstein. Back around 1915 or so, Albert Einstein published his famous theory of general relativity. One of the things that this theory was able to do is you could apply it to the universe as a whole and show that it was actually possible that space itself, the space of our universe, could be expanding or contracting with time, growing or shrinking, in other words. And sometime after that theory was put out, Edwin Hubble and others observed for the first time that, in fact, space is growing. If you look deep back into our universe, we find that everything is moving away from us. This is because the amount of space between us and these objects is growing with time. The universe is getting bigger. So that was exactly what people using Einstein's equations would have expected to find until back in 1998. These observations got a little more detailed, and they saw that not only was the universe expanding and getting bigger, but it was